Welcome back, everybody. Thanks for joining again. We're going to be checking out this example of this sled being pulled by a boy at an angle. There's a rope coming off of the sled, and he's being pulling it at an angle. So this is another good application of Newton's second law. And so let's just draw the sled here for a second. I'm going to make this sled green just because I have my green pen out. And I'm going to draw basically right from the side. We're looking at it sort of as a partly side, partly overhead view. This is right from the side right here, so it's sliding on the ground horizontally. And this force is being applied to it. And this force is being applied upwards like that. We're just going to call that our force F. It's the only force that is being applied to this sled. And it's being applied at an angle of 35 degrees. That's 35 degrees right there. This force is 6.2 newtons. 6.2 newtons? Or 6.20 newtons. Okay, and so we're being asked, and this is, again, this is a good Newton's second law question. How fast is it going? That means not what is the acceleration, but what is the actual final velocity of the sled after being pulled for a certain amount of time. Okay, so we're going to have some old kinematics equations in here as well, or at least some kinematics applications in here. In fact, let's write everything down, everything else that we know. It starts at rest. Okay, well, that's important. So initial velocity is 0 meters per second. Final velocity, we don't know, right? That's what we want to find out. We are being told, however, that the time it's being pulled for is 1.15 seconds. That's going to be important. It's going to be critical to this, to solving for how fast it's going to be going. So we have this sled right here. It has a mass of the sled. So I'm just going to write M sub S like that is 4.60 kilograms. And it's being pulled with this force right here. Okay, now this force is at an angle. It's at a 35-degree angle. It looks like 135. That's because I have that little arc thing in there. Let's just erase that. It's a 35-degree angle. And so whenever we have a force at an angle, the first thing we want to do is take that force and break it into an X and a Y component. So, the force itself is 6.2 newtons. The force in the X direction, that's going to be 6.2 times the cosine of 35 degrees, right? And we're using cosine like we're used to using because this 35 degrees here is based off of the horizontal, like we're used to. And the force in the Y direction is going to be 6.2 times the sine of 35 degrees. That's that right there. 6.2 cosine 35 is oh, there we go. Sorry about that. I know I had it written down here somewhere. I guess I could have just calculated it too. 5.08 newtons. 5.08 newtons. Now, we could calculate the force in the Y direction, but we really don't care about this. And here's why. Because we can see, I'll make the X green. That's force in the X direction, and the Y I'm going to make blue like we're used to. Force in the Y direction. There is a partly upwards component of his pull, right? Because he's pulling upwards at an angle. But you can see that it's not making the sled fly up into the air. No, this upwards pull of his of the string is working against the weight force of the sled, but it's not making it fly up into the air. So these forces right here are kind of working against each other in conjunction with the supporting force, you might say, from the ice. All right, so either way, it's not moving in the Y direction at all. By the way, we're going to give a name to that supporting force a little bit later. We're going to call it the normal force. But the reason we don't care about this y direction right here is because there is no motion in the y direction. It's only in the x direction. The sled is not flying up into the air. It's simply moving horizontally like that. So what we can do is we can say that the net force, really the only force that we care about is in the x direction. So the net force in the x direction is 5.08 newtons. Okay? But let's not stop there. Net force is 5.08 newtons. That's the only force really acting in the x direction. It's also true that the net force, and this is Newton's second law, is equal to the mass of the sled times the acceleration of the sled. In this case, in the x direction. There is no acceleration in the y direction. So when we're being asked about how fast is it going and the acceleration that causes that, we're talking about the x direction only. So this is true, but this is also true. So therefore, we can say that these must be equal to each other. We're going to be doing a lot of that in these force problems, setting the net force equal to an object's mass times its acceleration. I used up a lot of space there with those arrows. I'm probably going to need that space, so I'm going to erase them. So we can say, since we know that the mass of the sled is, 4.6 kilograms, we can say then that 5.08 newtons equals 4.6 kilograms times acceleration in the x direction. See what I did right there? Okay, kilograms, not K. I don't even know what that is. Okay, so the acceleration, must be in the x direction, 5.08 newtons divided by 4.60 kilograms. I do have it written down here, I think, but 5.0, I did it a little bit different. 5.08 divided by 4.6. 1.1 acceleration in the x direction equals 1.1 meters per second squared. All right, that's great. However, we want to find the final velocity after it's been pulled that for a certain amount of time with this acceleration right here. Well, that should be easy to find because we have an equation for that. We've got an old kinematics equation for that. Isn't this true? Final velocity equals initial velocity plus acceleration times time, right? So we know the acceleration of the sled. We just found that out by finding the net force and then taking that in conjunction with the mass and finding the acceleration. We have the acceleration. All we have to do is solve for the final velocity now. So V final is going to be V initial, which is 0, plus our acceleration, 1.1 meters per second squared, times time. Time is 1.15 seconds. So the final velocity that I get, 1.27 meters per second. That's our final velocity. We're using Newton's second law, force is mass times acceleration, in conjunction with some old kinematics equations to solve for final velocity right here.